All right, well, welcome to another Friday here in vector calculus. We're going to keep talking triple integrals today. We'll practice a little bit switching order of integration and start getting at what Victor kind of hinted at last time. You may remember he said something about, can we use polar in these triple integrals? We'll talk about the adjustments that we have to make when we go to cylindrical and spherical coordinates. So I'll give you kind of a reminder about how those things work as well. But that's what we're going to do today. We're just going to keep playing with doing triple integrals. The long-term goal, what we're going to hit next week, is going to be applications of the triple integrals. We'll start looking at, and double integrals. Like what do we actually use these for? Because so far it's pretty much been restricted to areas for double integrals, or volumes, I guess, and then for triple integrals, only volumes. But there are lots of things we can do with them, but we got to learn how to use them before we can look at, what they're good for. So that's kind of the long-term goal. But before we get to talking more about triple integrals, I want to open it up to you guys. Are there any homework questions you'd like to look at? Wow, none. All right. It's rare, but I will take it. Okay. So don't forget though that the next homework set is due on Monday night at midnight. So don't forget to get in there and play around with them. But I guess with that, then let me go hop to the whiteboard and we'll start talking triple integrals. And I said, start talking triple integrals. I really should have said, continue talking triple integrals, because we've already done a little bit of this. So let me just remind you kind of how these things work in terms of the setup. So the three integrals, we're going to be integrating a function of three variables. And we're going to have a dv. I'm just going to go ahead and write a dz, dy, dx, but it can be any combination of the three, right? Any order of those. But depending upon those orders, then we know what's going on with the bounds. These innermost bounds are going to be functions, in this case, of x and y. So I'll call them g1 and g2 of x, y. The next bounds out are going to be functions of x. So I'll call them h1 of x and h2 of x. And then the outermost bounds are just numbers a and b. And the way you can tell what variables you can have in these positions are from the order of the differentials, right? This first integral is an integral with respect to z. So that means x's and y's are constants, which means they can be part of the bounds. The second integral is with y. So that means that x's are the only thing that can be bounds. We can't have z's because z's are already gone, right? The z's have already been dealt with, so the only thing left are x's. And then lastly, we just have constants because the last integral can only be constants. All right, so here's our triple integral. I mentioned this before, but I want to bring it back up again, that there are actually 6 different ways to do this. You can actually order those differentials in 6 different ways. It's 3 factorial. That's where that number comes from. So any one of these things can be done in 6 possible ways. There are ways that are easier than others, but we actually have 6 different options. All right, so we're going to play around with them and decide how we want to do that. But we use Integration Man again to help us visualize what's going on. All right, so there's the basic structure. This is what they look like, and this is how we're going to play around. So with that, let's practice one. Let me put one up here. And this one's just going to be, no big deal. Just a simple looking kind of guy. It's going to be triple integral. And let's just integrate one. So we're not going to have a function there. But let me put the bounds on first. And I want you to see, I want to see if you can tell me what order we're taking the differentials. All right, so I've got bounds 0 to 1. That tells you nothing. And we've got root x to 1, and then 0 to 1 minus y. All right, so in the chat box or out loud, can anyone tell me what their guess is for the order of integration here?
Dx is the third one.
Okay, good. How do you know dx is the third one, Jordan, the last one?
Because on the second one, it's 1 root x.
Okay, so the first set tell you nothing, right? We know nothing about it from the first set of bounds. But the second set, since it's only x's, that means that x's are going to be the last thing that remains before we integrate. Okay, so good. So we know that dx is back here. Now, a couple people threw some stuff in the chat box. Actually, both Matthew and Jesus put dz, dy, dx. So if we were going to go with majority rules, that's what we would go with. Is that correct? What do you guys, what do the rest of you think? So Victor's backing you up. Ralph says he thinks that looks right too. I 100% agree. And here's how you can tell. So you look at the first set of bounds, they have a y in them. So that tells us that y cannot be first. Okay, well, if y can't be first, we already used the x, then we know it has to be a dz. So this is dz, dy, dx. All right, so let's go ahead and integrate it just for the practice. So we integrate the dz, we get a z. So we're going to get z evaluated at 0 and 1 minus y, which leaves us the integral of 0 to 1, root x to 1, of 1 minus y, dy dx. All right, so now we integrate with respect to y. We're going to get y minus y squared over 2, evaluated at the square root of x and 1. So plugging in those bounds, we get 1 minus a half, which is 1/2, minus root x plus x over 2. So watch your signs on these, but this is a minus and then a plus because when we subtract, we're changing the signs. All right, so then lastly, we integrate with respect to x. That gives us a 1/2 x minus 2/3 x to the 3/2 plus x squared over 4 that we now evaluate at 0 and 1. The 0, of course, is going to give us zeros. When I plug in 1, I get 1/2 minus 2/3 plus 1/4. So that's 3/4 minus 2/3, which I think is 1/12. I am entirely not confident on that, but we'll go ahead and put that in a box because, what the hell, go huge or go home. Okay, so that's the process. Once we've got one of these things, it's just a matter of integrating. They do get long. You saw the one that there was that one that we did last time that it was really tedious once we got to the end. And that will happen. It really just depends on what the bounds are and what your original function was. But this one is 1/12, which means if we were to actually figure out what shape is bounded by these, we just found the volume of that shape. All right, so far so good. Good little reminder of how this all plays out. All right, I got at least, there's a couple of thumbs up coming. Okay, good. So this is the general process, no big deal. Okay, but now let's do this. Let's go back to this original triple integral, right? The one that we just calculated the value for. I want to see if we can get a picture of the region in space over which we're integrating. Because with triple integrals, that's what we're doing. We're looking at some solid region in space over which we're integrating, or in this case, we're finding the volume of that region in space. But let's see if we can picture it. I want to do this so that we can swap bounds. We're going to change the order of integration on this. But in order to do that, we have to have kind of an idea of what this looks like. Okay. All right, so how are we going to do that? Well, my recommendation, if you're going to try to picture this, is just start with what these things actually mean. Start with the inner bounds. So this 0 on the bottom, this is a z equals 0. This one on the top is z equals 1 minus y. Now, the reason I want to write it out like this is because these are the surfaces where integration man's feet touch and head touch. So the entire time integration man is walking around, his feet are always on z equals 0. And his head is always resting up against z equals 1 minus y. All right, so basically, we're defining the floor and the roof, for lack of a better way of saying this, right? You can think integration man is walking around in this volume. It's like a little room. Well, this is the floor, this is the ceiling. Those are the surfaces that he's touching. Okay, so what is z equals 0? Let's start with the floor. What surface is z equals 0? Okay, so Victor says it's a plane. Cool. What plane?
The XY plane?
Like. What are z equals planes?
Vertical ones?
All right, not vertical, but you're thinking the right way, Bradley. So z equals, those are ones that are parallel to the xy plane. All right, so think about the xy plane. Z equals are the ones that are parallel to it. I like to get away a little bit from vertical or horizontal. I just say, Jesus just put in horizontal, because it kind of depends how we set it up, right? If we're going to use like the whiteboard as the xy plane, then z equals are vertical. But there's a difference between being vertical like this and vertical angled, right? Or vertical that way. That's why vertical doesn't really work very well. And the same issue with horizontal, right? So better if we start talking about them in reference to the coordinate planes. So z equals 0, that's actually the xy plane. So if you ever have a one of the letters equaling 0, then the plane, it's the coordinate plane that's made up of the other two. So like if we had y equals 0, that's the xz plane, and so on. Okay, so I suggest that when we talk about these and when we try to visualize them, let's make z be up and down. Okay, because I think that's more natural for us to think, z being up and down as opposed to coming in and out of the board. So let's go z up and down. So I'm going to continue to use my room to help us with this. So remember when we did the example of the tetrahedron and we talked about like the walls and the floor in my room? So my floor is z equals 0. All right, so we'll specify that that's z equals 0. So integration man is just walking around in my room. At least the floor is that way. Okay, so what about the ceiling? What kind of shape is z equals 1 minus y? Okay, so that is another plane. How do you know it's a plane? Because some of you are putting question marks on there. And how do you know it's actually a plane and not something else?
My guess is just because we're in 3 dimensions.
Yeah, we are in 3D. Like this would be a line, right? If we were in 2 dimensions. If you extend a line into 3 dimensions, it becomes a plane. Another way to recognize planes is that there are no powers on the variables. They're linear. So if your equation is linear in the variables, then it's a plane, right? It's just z to the first, y to the first. We don't have any squares or cubes or square roots or anything like that. So that's also a plane. All right. Where's it point? What direction does it go? And all that. I saw just a minute ago, Victor put negative slope has negative slope. We want to kind of be careful about that because planes technically don't have slope. Right? Lines do, but planes don't. But it does make sense to us about a negative slope as opposed to a positive slope, even with a plane. Let me grab a plane real quick. Also known as a notepad. Okay, but here's our plane, right? So it makes sense for a plane to be like sloping up or sloping down, right? So we can think of that positive, negative slope. However, okay, does this have positive or negative slope?
Positive.
Okay, you want to call it positive slope? Does this have positive or negative slope?
It depends.
Right, because if I keep turning positive or negative slope, now you're going to say negative. Well, what about here? Right, so I'm keeping the same angle. I'm just rotating it. And at what point does this positive slope turn into negative slope? You know what I'm saying? So it's not as easy because of the third dimension. So here's how I want you to, or some things to think about with planes. First of all, look and see what variables are in there. If there's just the one variable, like the z equals 0, those are going to be parallel to the coordinate planes. Okay, so z equals, these are z equals. They're parallel to the floor. X equals, y equals. Okay, well, let's go with the whiteboard wall is y equals. That's the x. Let's say that this is the, how did I have, no, this is the xz plane. So that would be y equals 0. So these are all y equals planes. And then these are all x equals planes. Okay, so if you have just one, they're parallel to the 3 coordinate planes, the floor or the 2 walls. Okay, if you have just 2 variables, that means they don't intersect one of the axes. Okay, and the axis that it doesn't intersect is the one whose letter is missing. So this plane, it does not touch the x-axis. Okay, so that plane it does not touch the x-axis. If there was no y, it wouldn't touch the y-axis. If there was no z, it wouldn't touch the z-axis. Okay, so again, think about my room and how this is set up. The x-axis is down here at the base of the wall. Sorry about that. Okay, that line, this border right here, that's the x-axis. The one over on the wall there, that's the y-axis, and then the z-axis is the one going up through the seam, right? Okay, so with that being the x-axis, that means that this plane can never cross through that line, which means this would be a problem. This plane would intersect it, right? This plane would intersect it. This plane, however, would not. This plane would not. That plane would not, right? Basically, think of the axis. Let me make another axis here with my pens. So we're going to turn our worldview a little bit, but this is the x-axis, let's say. This plane has to be such that it never crosses it. So if you're missing one of the letters, it means it doesn't cross through that. So if there was one with just x and y, it would never cross through the z-axis. So it would have to be, I guess, vertical, the way that we think about it, or so on. All right, so that's what happens if you got two variables. If you have all three variables, it slices through every axis. And a good example would be that one we did last time with the tetrahedron. Remember that surface that formed the triangle that was the sloped roof? That one was a plane that had an x and a y and a z, so it will intersect all three. Another way you can think about it is think about what z equals 1 minus y looks like in the yz plane. Z equals 1 minus y would look like this. Since that doesn't matter what the x is, it'd be like taking that line and sticking onto it a line here and a line here and a line here and lines forever back and forth. And so what we end up getting is this plane right there. Okay, so my notepad here is the plane z equals 1 minus y. And you notice that it will never intersect the x-axis. There's the x-axis coming out as pen, right? And it never crosses. All right, so let's get back to the integration man and what this looks like. Now I'm going to try to draw this in 3D. I'm going to do my best. All right, so here's our x, our y, and our z. And so what we have is a plane yeah, that's pretty horrible. Okay, well, let's look at it from the side. Okay, so this is the side view. So here's z equals 0, and here's the z equals 1 minus y, and integration man is doing this. So it's like a tent, right? It's a sloped roof that's coming down. All right, so that's great, but now we need to figure out over what part of the floor is he walking. And so that's where we're going to turn our attention to these two. Now, this part's going to be easier for us. It's going to be way easier for us because this is happening in the XY plane and we're used to drawing in the XY plane. Okay, so here's our X and our Y, and let's look at what we've got. We've got Y equals the square root of X and Y equals 1. So Y equals the square root of X does something like that. And Y equals 1 does something like this. So his feet are on the square root of X and his head is on 1. And this goes from 0 to 1. Well, that's this. So he's walking over this little region. His feet are on the XY plane. And his head is on the plane. Z equals 1 minus Y. And remember what that looks like. It's sloped. And it's sloped going from Z equals 1 up here down to Z equals 0. So I'm going to cover up the picture for a second, but it's sloped like this. So I don't know if you can picture that. This is where I really wish I could be in the room with you and we could be fiddling with some Play-Doh or something. But just think it's like a wedge. Let me get my hands angled the best. Okay, there we go. Okay, so it's a wedge. Z equals 0, Z equals 1 minus Y. We're taking that wedge and we're cutting it down with this shaped cookie cutter. Right? So there's that shape is coming down and slicing through that wedge. So it's starting, it's going up as we move in this direction. So imagine that this is coming out towards you a bit. So the thickest part of this wedge is going to be down at the end of my pen. And the thinnest part is going to be down here at the non-writing side. So it's getting thicker as we go. Okay, so that's what that shape looks like. Its volume is 1/12. At least I think that's what we calculated. Its volume is 1/12. But here's what I want to do. I want to see if we can change the orientation on this. Let's change this. So instead of doing dz, dy, dx, let's see if we can get it set up as a dy, dx, dz. So we're just turning integration man around. All right. So here's how I want to try to visualize it. I'm going to go ahead and use this orientation for right now. Again, remember that the way that this is set up is that this is the y direction. This is the x direction. And so z is coming out towards you. Okay, so now let's think about integration man in this surface. So integration man is going to be standing in the y direction. So at one point in time, integration man is going to look like that. Another point in time, he's going to look like this. But also realize that this shape came out of the board. So there are going to be times that integration man is away from the board, but still oriented up and down. Okay, now let's think about what this surface looked like. It was basically this room, but with a sloped ceiling. So right now, integration man, his feet are on this square root, the y equals square root of x. And his head is on the line y equal 1, but that y equal 1 is where two surfaces came together, right? Where two of those walls came together, where the sloped roof met the floor. Now, if we bring integration man out a bit, so think about this little short integration man, but we pull him away from the wall. What's going to happen to him? So his feet are still going to be on this y equals square root of x. But his head is going to start bumping into that sloped ceiling, right? So his head's going to start hitting that plane. And the same thing's going to happen for this taller integration man. As he starts walking out, he has to shrink because that roof is pitched. Are you kind of seeing what I'm saying? Like, think about how I've got, here's our pitched roof, and the feet are always on some surface here. So if I'm sticking out this way, I can be tall. But as I move upward, I have to get shorter to fit within that room. And that's exactly what's happening to integration man, because this curved surface, that came from our cookie cutter, right? We cut down with that. So we're going to see that shape forever on the way up. But this line didn't come from a cookie cutter. That came from that sloped plane. And so the head is going to change. So in terms of the bounds for y, his feet are going to be at y equals square root of x always, because they were on that cookie cutter slice. But his head is always going to be stuck on the z equals 1 minus y. But if I solve that for y, I get y equals 1 minus z. So hopefully you can kind of picture what's going on there. And this is why I'm saying 3D models are the best. If you can construct something with clay, Play-Doh, something like that, it will definitely help you see the orientation or see where things are. Because the other thing you can do is then you can use like a paper clip and stick it through, and think about that paper clip being integration man's body, and you can literally see the surfaces that it pokes through. So I highly recommend getting some of that. Okay, well, good, I guess, right? We've now got this part figured out. We know what's going on with integration man in the y direction. His feet are on this curved surface, and his head are always on that plane. Z equals 1 minus y. Okay, so now we got to deal with the x and z. All right, now let's think about x, and we'll go ahead and just use this picture for a second, where we were in the xy plane, because now we need integration man this way. And of course, integration man is going to be able to walk all around all the different locations, but I want you to think about him in this direction. Like right now, what's forming his head and what's forming his bottom? Well, his bottom surface is the y-axis. It's always the y-axis. And his head surface is coming from this curved plane again. Now, what if we move him upward? Because we have to allow for that, right? He has to be able to go in different z's. What happens if we move him upward?
He gets taller.
Is he going to get taller? For him to get taller, that would mean that the surface that's creating his feet has to move away, or the surface that's creating his head moves away as well.
He's going to get thicker. Like he's going to expand almost outward towards us.
Okay, so let's not think about him expanding outward. Like he's just going to move outward. But let's think as he moves out towards you, is his height change?
Oh, out towards us? No.
Yeah, it's not going to change because remember how this curved surface was formed? That came from the cookie cutter, which means that's going to extend out in the z direction.
I'm just too used to thinking of like the term up as meaning like in the y direction. So
Yeah, but so here's that surface, right? Because that cookie cutter came down and just sliced through that. So if integration man starts moving out with that, right, towards you, I'm going to angle it a bit so you can actually see towards you. But if this guy comes out towards you, his height's not going to change because his head is always up against this curved surface. And similarly, his feet, that came from the cookie cutter because we also sliced down through this, right? This green shape was the cookie cutter. So in this case, his head and feet are always on those two surfaces. So we need to think about those as x equals surfaces. So let's think about his feet. What are his feet? What's this surface as x equals? What would that line be? Okay, so Victor, yeah, so it's x equals 0. This line is x equals 0, and if it extends out, it's still x equals 0. So the bottom bound here is going to be 0. This other surface, right? The question is, what is that going to be?
is that root x or?
Okay, so that would it's y equals square root of x. But I can't have y equals square root of x.
X equals y squared.
Okay, so because we want it as x equals, we realize that this is x equals y squared. But I still can't have x equals y squared. What's wrong with that?
We need to define it in terms of z, don't we?
We absolutely do need it in terms of z, because remember the y's are already all used up. Well, how is y related to z out there?
Y is orthogonal to z. Oh, there we go, Victor.
Okay, so Victor just said y equals 1 minus z. Yeah, you remember that, this surface? Because remember what we're doing, we're intersecting this curve with the surface, with the plane, right? And where things intersect, we can set those equations equal to each other. So we substitute in for that y with a 1 minus z. So that line, if we think of it as an x equals, but in terms of z, is x equals 1 minus z, quantity, squared. All right. Well, I guess. So all that's left then is to figure out what z's does integration man walk over. So he clearly is on z equals 0, xy plane, but how far out does he come? What's the biggest z we're going to see with integration man here? How far out does this surface come?
One.
All right, so Bradley says 1, but doesn't sound like a lot of confidence in that 1.
No.
Why do you think 1?
Because I had a reasoning, but now I'm not sure.
Well, try it out. Let's hear your reasoning, and maybe like we'll be on board.
Well, if z equals 1 minus y, and the highest y we get is 1. No, that doesn't work. No, I don't know.
You were totally on the right track, though. Think about that plane. Remember that plane is sloped like this? So the highest point is going to be when we're at our lowest y. Yeah?
Yeah.
Okay, so what's the smallest y we can get in this region?
0.
0.
0. So if the smallest y is 0, that corresponds to the biggest z, which is 1.
Oh, cool.
So you were right. It is 1. And that's how we know. All right, so this would be swapping the bounds, swapping the order of integration for this guy. Okay, so let's just pause for a second. Let me come over here. I'm tired of kind of being at an angle. All right, let's have some real talk with Bruce here for a second. Okay, so we did this, and for a lot of you, you're probably like, holy shit. If I have to do this on my own, I am screwed. Is that pretty accurate feeling right now?
Yeah,
Yep.
sounds good.
Okay. It's not just you. Everybody, first time they see this, these are the feelings that you have. Okay. So these are challenging, even for relatively simple bounds. I mean, look at the original bounds. Those were not crazy. Lots of zeros, things that weren't zeros or ones, right? Zeros and ones, nice. Those that weren't zeros and ones, not terrible. Square root of x, that's not that bad, right? The 1 minus y. Okay, so even with something that's not that bad, or doesn't look that bad, can get a little challenging when you're trying to do this. Okay, so some advice. Number 1, build the models. Practice building these things, looking at the surfaces. Know your surfaces. Know your surfaces. But also notice that what we did was we made use of the algebra, right? Like, come back to this one where we're going, oh, his head is always on the y equals square root of x. But we went, nope, we need x equals. Okay, boom, x equals y squared. But then we went, nope, can't have y's. Because the order here, we already used up the y's. Go back to the relationships that we already have, and that can help you out a lot as well. So pay attention to the algebra, how things are related, and also pay attention to the order. Oh my God, the order is so important. It tells you so many things. Not only does it tell you how to start orienting integration man, but it tells you those other little things like the solve it for x, not y. Can't have y's, got to have z's, right? Those little things can help you get where you need to go. So we'll continue to talk about changing the order of integration as we go along. But these feelings that you have right now are 100% normal. Almost everybody feels them at this point where you're just like, man, I don't know. But look at examples, practice them. The more you do, the easier it's going to come. He says confidently, right? Okay. Well, anyway, so there's another triple integral. So let's do another one. Let's find a volume of a shape that doesn't have 0 as the bottom, because we've been doing a lot of those. But let's go to one where we don't have the xy plane as the bottom. And for this one, let's find the volume of this shape. What I want is basically a cone, but on top of that cone, I want a spherical top. Okay,
So an ice cream cone.
So it's definitely an ice cream cone. All right, so it's a sphere on top of a cone, or at least the portion of a sphere on top of a cone. So this would be, how much ice cream do we have in this ice cream cone? All right, if we jam it full, what's the volume of this shape? All right, so that's what we're going to look for. Now, it's going to help if we actually have equations for these things, right? So let me do that for you. All right. So the cone has an equation of z equals, or well, actually, let's go to, no, not z equals. Let's write it the way that we're used to seeing cones, which would be x squared plus y squared minus z squared equals 0. So real quick reminder for you for quadric surfaces. You know it's a cone if all 3 are squared, one of them has a different sign, and it equals 0. Okay, so that's always going to be a cone. If they have different numbers in front of them, it's an elliptic cone. The cross section is an ellipse, not a circle. So like a waffle cone, a handmade waffle cone is going to be more elliptical cone shape, as opposed to the ones that you buy from the grocery store that are nice circular cross sections. Okay, but anyway, so there's the equation of that cone. All right, well, I also need to give you the sphere. And this sphere is just the unit sphere. So it's going to be x squared plus y squared plus z squared equals 1. So in terms of the coordinate axes, the z-axis goes right down through the top. And then your x and your y are doing this, right? So we got our ice cream cone, and it's just set so that the tip of the cone is at the origin. All right, so far so good? We cool with what we're trying to do?
Yeah.
All right, I'm seeing thumbs up. So, all right, so let's see if we can get it set up. So we're gonna do a triple integral. Since we're just finding volume, we're integrating 1, so we'll just leave that like that. So what we have to decide first is which way do we want to set up our bounds? Do we want to go z first, x first, y first? Which one do we want to do first? So what do you guys think? Do you have a preference here?
No. Don't have a preference.
All right. So Bradley says no. Victor says he would like to do dy dx dz. So y first, then x, then z. Why that preference, Victor? Why do you want to do y first? And you sound like one of my kids. Cause I wanna. What? So Ralph just said, how about dz dy dx? So kind of like the one we just did. You have a reason for that one, Ralph, or is that also just cause, or because you want to be different? Okay, so we got some answers here. Victor says he's used to having y first, so that's why he wants to start with y. Okay, I can appreciate that. And then Ralph, you're saying you want to do the z because of the z squared, the minus z squared. And I'm going to go with, because that it's going to be easier to solve it for z. Is that what you mean? Yeah, okay. When it comes to actually solving for any of them, they're pretty equivalent. I mean, yeah, like for the z, we only have to move the z over and then take a square root, as opposed to if we're going to do the x, we got to move these two things over and take a square root. But for the most part, solving for one or the other is not that terrible. But let's look at the picture and let's think about what happens if we do the different directions first. So let's think about like dy first. That was the one that Victor threw out because he's used to having y first. Okay, so if we're going to have integration man be in the y direction, he's going to be oriented this way as he's walking up and down and left and right and all that good stuff. Okay, so at this point, like you just look at this one right here, what determines his head and what determines his feet? Which surface?
It's both. Like,
Both are defined by the cone.
Okay, so
yeah.
it's both defined by the cone. That already tells you something. If you ever have both head and feet defined by the same surface or same curve, then that means that when we solve, right, because we're going to have to solve it for y equals, one of them is going to have to be the plus, the other is going to have to be the minus, right? Because when we take the square root, we get a plus or minus square root. So we already know that that's going to happen if we do it this way. That's not enough for me to wave you off and say, "Ooh, yeah, that's a problem." That's not a problem. It's just something to recognize. But the real issue is what happens when he gets a little bit higher.
He hits the sphere.
Yeah, and then
Eventually,
then he's defined by the sphere.
he's got head and feet both defined by the sphere. Well, okay, both defined by the sphere means same thing. We're going to use plus square root minus square root. Again, but the real issue is this means two integrals. If we set it up with dy first, we're going to have two integrals. One for when his head and feet are on the cone, and then at this point we swap it so that head and feet are on the ice cream. I don't want to do that. So that would definitely make me think not to do dy first. It's still possible. So Victor, like you say, you want to do y first because it feels more comfortable. Go for it. Just realize that in this case, you're going to have to end up doing two different integrals.
Now, when you say two different integrals, you mean two different triple integrals, right?
Correct.
Okay.
Yep.
Yeah, nah.
Yeah, when I say integral now, I mean triple integral. Even though the triple integral is made up of three partial integrals, altogether it's the integral. So yeah, you would take two triple integrals. You'd have to set one up for the bit when he's in the cone and another one for the bit when he's in the hemisphere or in the sphere. Okay, so that's what's going to happen if we do y first. All right, let's think about the other options. Let's real quick talk about x. What if x is first?
I think it's going to be the same.
Yep, it's entirely the same. It's just because of the symmetry of this. Now integration man is coming front, kind of in this direction. Same kind of thing. Head and feet are both on the cone, and then they both end up on the sphere. Same thing, 2 double integrals. So I don't like that. Which then leaves us z, right? And so Matt just said, well, so z it is. Let's not necessarily just jump straight to, okay, yeah, z is the one we want, because it might also lead to having to do more than one triple integral. But let's look at z. So let's get rid of integration man here, and let's go integration man vertically. So when he's somewhere inside here, so like that piece right there, his feet are on the cone and his head is on the sphere. Is that always going to be the case? That his feet are on the cone and his head is on the sphere?
Yes.
Yes.
Yeah. No matter where he walks around in here, it's always going to be that way. Again, think about the ice cream cone. Most of us have experienced an ice cream cone. If you haven't, I apologize. Next time we get together, I will make sure you get your first ice cream cone. But if you've ever experienced an ice cream cone, think about taking a paper clip or a thin wire or something and poking it straight up and down. You're always going to see the top of it sticking out of the ice cream. And the bottom is always going to hit the cone. Integration man's head is always going to be on the ice cream, on the hemisphere, and his feet are always going to be on the cone. So, yes, Matt, z it is. Let's do z first. Okay, so in terms of the other ones, we'll worry about that in a second. But let's just start with z first. Because then I only need one triple integral. I just need the sphere on top and the cone on the bottom. So that means we do need to solve these guys for z. Well, that's not that difficult. So the first one, we're going to get z is equal to plus or minus the square root of 1 minus x squared minus y squared. But we do have plus or minus, and I can't have plus or minus. I need either the plus or the minus. So which one am I going to use? The plus or the minus?
The plus,
The plus. And why, Jordan?
his volume is always positive.
Actually, that's not the reason I'm going to use the plus. But you are right. Volume is going to have to end up being positive.
We don't go negative in z at all.
Yeah, if you think about where this cone is, it's above the xy plane.
Oh,
which means
yeah.
these are always positive. If we had the negative is the bottom half of the sphere. So since we're on the top half of the sphere, we're going to use the plus.
Go polar.
Polar.
Yeah. Or I guess cylindrical.
Well, we'll talk about that here in a second.
It's just, I don't know. I can't help but see that as 1 minus r squared now.
Good. I'm actually glad that you see that. Because you're right. If we were doing something in polar, make that 1 minus r squared. You definitely want to do that. I don't know that it would simplify things so much here, but I'm glad you're seeing that and thinking that, Bradley, because that's going to serve you well. All right, well, let's do the same thing for the bottom. The bottom, if I solve this for z, the cone, it's plus or minus the square root of x squared plus y squared. So same question, plus or minus. Well, it's the same answer. It's the plus. And if I were to ask you why, it's the same answer, because this part of the cone is above the xy plane. We're in positive z world. All right, so far so good? Thumbs up? All right, thanks for playing along. All right, so now we get to do the old dx and dy, or dy dx, which way do we choose? So what we need to think about now is the shadow of this shape. What is the shadow of this on the XY plane?
Circle.
Okay, so it is a circle, right? If we were to extend it out, we're going to see that there's the shadow down here is a circle on the XY plane.
It's the unit circle, right? Because it's a radius of 1, centered at the origin.
Okay, so is it the unit circle? Turns out it is not the unit circle. And here's why. This was the unit sphere. So the sphere has radius 1. So imagine we were to bring that sphere down. That would be a radius 1 circle, right? Where the sphere comes down, but we're not seeing the entirety of the sphere. Scheisse. So what do we do? How can we figure
Find
out? I'm sorry,
what
go
the
ahead.
radius of the circle at the top of the cone would be?
That would definitely do it. If we found out this circle where the cone meets the sphere, that is going to be the same circle that forms our shadow. All right, awesome. Nice call, Jacob. So how are we going to do that?
Well, first find where the sphere and the cone intersect.
Beauty. Let's do that. So if we look at those two equations, we basically need to solve this system. We've got x squared plus y squared plus z squared equals 1. And we've got x squared plus y squared minus z squared equals 0. So to find the intersection, we just solve that system. I wrote it this way on purpose, because how about we just add those suckers together to get rid of the z? So we get 2x squared plus 2y squared equals 1, or x squared plus y squared equals 1/2. So that's the equation of the circle where the cone and sphere come together, which is the equation of the circle on the xy plane over which integration man has to wander.
So the radius is equal to 1 over square root of 2?
Correct. All right, so since it's a circular region, it doesn't really matter whether we do dx dy or dy dx. So let's just do dx dy. So if we do dx dy, we need to solve this for x. So x is plus or minus the square root of 1/2 minus y squared. So if we're doing this in the x direction, so here are some integration men. The head is always on one of the semicircles and his feet is always on the other. So it's going to go from the minus square root of 1/2 minus y squared up to the positive square root of 1/2 minus y squared. And then the bounds on x, those are the radius of this, right? So as Jacob saw, since r squared is equal to 1/2, r is equal to 1 over root 2. So the x bounds are then going to be minus 1 over root 2 to plus 1 over root 2. So if you do that integral, you will get the volume of that. That's how much ice cream will fit in that cup. All right, so I did this example for a couple of reasons. First, just to kind of talk through how do you decide which of the 6 orders? I mean, we got a bunch of choices. How do we pick which one, right? So hopefully you kind of got a feel for that. And I think it also helps you kind of visually see integration man and all that. But the other reason I did this example was one that Bradley already kind of caught on to. Wouldn't it be so much nicer to be doing this in polar?
Yeah.
I mean,
Yeah, especially cylindrical.
forget about like the surfaces, but even if you just look at the region over which it's, you know, he's walking in the XY plane, it's a circle. Oh my God, if we could have done that in polar, R's go from 0 to 1 over root 2, thetas go from 0 to 2 pi, done. Right? So this is a perfect example of something that argues for what about using one of the other coordinate systems for 3D? So let me remind you about those other two systems. They're called cylindrical and spherical. And then I'll show you, I think we've got enough time, I can at least show you what happens if we do this in cylindrical. All right, so real quick, to remind you about these guys. Cylindrical. This is the one where we have R, theta, and Z. Basically, it's polar, just extended out in the Z direction. So the R and the theta, those are the same R's and thetas as from polar, and Z is the same old Z. Okay, so we've got R, theta, and Z. So in terms of the conversions, X is R cosine theta, Y is R sine theta, and Z is Z. And we also have the reverse conversions that R squared is X squared plus Y squared, and the tangent of theta is Y over X. So cylindrical is not usually that big of a deal for folks. If you've got your polar down, it's okay, polar, and then just attach a Z. Okay. So that's cylindrical. The other one is spherical. And in spherical, what we've got is a rho, a theta, and a phi. So this is one distance and two angles. Okay, so theta is the same theta. It's the same theta as from polar. Rho, that's your distance from the origin. And this is a three-dimensional distance, right? So like if the origin is this corner right here, let's go to corner of the whiteboard. So like, let's say that this is the origin, and I've got a point out here. Rho is literally just the straight line distance. If I just connect these two, that's rho. So if I move it over here, that's rho. Move it in here, this is rho, and so on. Okay, so rho is just distance from the origin. Theta is rotating in the XY plane. And then phi is also a rotation. And does anybody remember how phi works?
Phi is the angle from the z-axis, right?
Yeah, from the positive z-axis. So if we've got it like oriented here, you rotate from the positive z-axis, and that's your phi. So like we can really see it well on this picture. If we talked about, say, look at this point of intersection of the cone and the sphere. I can actually show you rho and phi super easy on this picture, because rho would be this distance, right? It's how far is that point away from the origin. And then phi would be this angle, rotating from the positive z over to that point. And then theta, well, theta is going to depend where this is. If we were to project it down onto the plane, like let's say its projection was here. Okay, so that's this point coming down is right there. Then that would be your theta. Right, so theta is in the XY plane like we're used to, but phi is coming from the positive z. All right, so that's those guys. That's what those three are. Now, they also have conversions. Right? So just like x and y can be written in terms of r's and thetas and stuff in cylindrical, they can also be done the same way in spherical, but it's a little bit more complicated. It's rho sine phi cosine theta for x. Y is rho sine phi sine theta. And z is rho cosine phi. Now, if you want a little help remembering them or finding them, let me first just point your attention to the fact that if you're good with the polar cylindrical, notice how this x has cosine theta, y has sine theta, same thing. Those still have the cosine theta and the sine theta. So then how do you know about the rho sine phi versus rho cosine phi? Well, I actually used this picture. Look at just sort of how I have this drawn, and look at this triangle in red. So I know this picture has gotten kind of messy. But looking at that triangle, here's the z. And notice that if you use phi, z is the adjacent side, rho is the hypotenuse. Adjacent over hypotenuse is cosine. So the cosine of phi is equal to z over rho. So z is equal to rho cosine phi. If you use sine, sine gets you this guy, which is r. So similarly, right, with the x's and the y's, you can use the fact that r is equal to rho sine phi, and then just substitute that in. So that's how I remember it, but you guys know I'm a huge trigophile. I love trig, so everything to me is trig. It's not hard for me to picture it. But regardless, these are your conversions, okay, for spherical. There are also the reverse conversions. Rho squared is actually equal to x squared plus y squared plus z squared. It's the same idea, right? It's the distance formula in 3D. So that's rho squared. For tangent or for theta, you can do the same thing since it's the same theta. So tangent of theta, that's equal to y over x. And then for phi, the easiest way to do this is to use this last one, and you get that the cosine of phi is equal to z over rho. So the cosine of phi is equal to z over the square root of x squared plus y squared plus z squared. I'm going to be 100% honest with you. I never, ever, 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 ever use this conversion. Never. I use the rho squared equals x squared plus y squared plus z squared a lot. And the tangent of theta is not very often, but kind of. The cosine of phi, never. I'm just putting it there for completeness. But these green ones, oh yes, we use those a lot, a lot, a lot, a lot. All right, so there are the kind of the nuts and bolts of cylindrical and spherical. But let me show you, at least with the cylindrical, because I think that's, yeah, I think that's all the time we've got for today. Let me show you how this thing, if we apply cylindrical to it, makes this a lot easier. Okay, so first, I'm going to erase this because we don't need this in rectangular anymore. First thing I want to do is let's convert these equations into cylindrical. Okay, so here was the sphere again. Remember, the sphere was x squared plus y squared plus z squared equals 1. So if we change that so that we're now in cylindrical, the x squared plus y squared becomes r squared. The z is still z. So we get r squared plus z squared equals 1. Okay, that's easy enough. Similarly, we can take the cone and do the same thing. So for the cone, we had x squared plus y squared minus z squared equals 0. Well, if we convert that, this becomes r squared minus z squared equals 0. Okay, so there are your conversions. Now, when we set up this integral, we still want to do it z first, right? So we want to do a dz, and then we probably want to do dr d theta. But, we know that there's likely to be something in here.
Another R.
Okay, because in polar we had r, right? With the polar we had to go to r dr d theta, right? So are we still going to get an r? Or as Victor just put in, are we going to get an r squared? Are we going to get a... Okay, well, let's hold on to that for a second. But let's just keep in mind that we do have to figure out what goes in there. I mentioned before, we call that a Jacobian. What's the Jacobian? I mean, sometimes you get lucky and the Jacobian is 1. You barely get lucky. Usually it's something else. So we have to worry about that. But we'll look at what a little volume chunk in cylindrical looks like so that we can figure that out. But barring that, let's at least go to bounds. So if we still do z first, integration man is vertical, his head is going to be on the sphere, and his feet are going to be on the cone. So we need to solve these things for z, like we did before. Well, the sphere, it's going to be the square root of 1 minus r squared, like before. His feet, check this one out. We solve this for z. We get r squared equals z squared. So what does z equal?
Plus or minus R.
Okay, so plus or minus r, which one are we going to use? Plus or minus?
Plus.
Plus, because we're above. So this is just z equals r. Oh, beautiful. Okay, so those are those bounds. Now, you remember what they looked like before. Well, those are our bounds now for z. So now we go to the r and the theta. Well, the region in the xy plane is just a circle. So we can use just good old r's and thetas. So the r's are going to go from 0 to 1 over the square root of 2, because that was the radius of that circle. And then the thetas, since we're getting the whole of the circle, go from 0 to 2 pi. So barring some absolute weirdness in this Jacobian that comes from our little volume chunk, you should all be much happier with the bounds on this triple integral.
Oh yeah.
Right? And Bradley, because you were the one who spoke out about this, and I'm sure others of you saw it, but I'm going to give you the kudos here. You know, good job on seeing that, man, if we could just go to polar here, it'd be a lot easier. Well, there is a 3D equivalent of polar. And so if it feels like you want polar, but you're in 3D, do cylindrical. Totally. Because you can see that it simplifies things out. Okay, well, we still need to figure out what is that little change, what happens when we go to a change here with our little dv. Well, think about how we did that before. we drew a picture of the little differential chunk and tried to figure out what its volume would actually be. And so when we did it in polar, remember what we had was like the crust of pizza. So we had a d theta, and we also had a dr. But because it wasn't a rectangle, that's what gave us the r, dr d theta. Well, let's make this three-dimensional now. The other differential here is z. So a dz is literally a up and down. So remember that little crust of pizza, the 2D crust of pizza? Well, now just pull it out. Okay, so what does that dz do to the volume here? Well, it does exactly the same thing as the dz did to a dx dy, right? Like if we had a little dx and a dy, and we extended it in the z direction, same thing happens, right? It's just that same area, but multiplied by dz. So here's what's really nice. In cylindrical, it's that same r. That's it. So in polar, it was r dr d theta. In cylindrical, it's r dz dr d theta. And just throw in a dz. So most people really like cylindrical because there's nothing really new to learn. You just throw in an r when you change your dv. The z's, well, it's still z equals. You just convert everything, get rid of all the x's and y's. And then it's business like usual. So when you're in a situation like this where you've got specifically regions, if the shadow that you're integrating over, if that region is asking for polar, go polar. Just do it. And in fact, let's actually do this calculus now. Let's figure out what this is equal to, because this is going to be easy enough for us to do. But before we do that, any questions on how I set that up? Are we good? Thumbs up? All right, cool. Seeing lots of thumbs up. All right, so let's calculate this and find out what the volume of that ice cream cone is. So we integrate with respect to z, which gives us a z. So we're going to get 0 to 2 pi, 0 to 1 over root 2, rz from r to square root of 1 minus r squared, dr d theta. Plugging in those bounds for z, we're going to get r square root of 1 minus r squared minus r squared dr d theta. All right, so now we get to integrate those two with respect to r. Well, the r squared, that's easy. That's r cubed over 3. And the other one's actually not as bad as you might think, because you can do a u sub. If u is equal to 1 minus r squared, then du is minus 2r, so we're only off by that minus 2. So we just have to adjust by a factor of minus 2. So to a 1/2 power, that would give us to a 3/2. So we're going to get 1 minus r to the 3/2. We would have to multiply by 2/3 normally. Whoops, there should be an r squared in there. Hold on. right? So normally we'd have to multiply by a 2/3. However, because of that minus 2r, we're going to get a 2 from that. So it turns out this is only minus 1/3 times 1 minus r squared to the 3/2. Do the u sub and you'll get there. Okay, so now I can plug in those numbers. I'm already bored with this. But this is just going to be a plain old number, right? Then when we integrate with respect to theta, we're going to get 2 pi times this. So it's going to give us 2 pi times the result of that integral. How's that for lazy? It's actually not too bad because when we square this, it just becomes a half, and you know, but again, not too lazy to do that right now. But notice how much easier this became as soon as we went cylindrical. Let's do the 3D form of polar. Bam, can knock it right out, right? The integration was easy. What got hard here was doing the substitution in, actually calculating the stuff, right? But the integration was fast. Compare that to what the integration was going to be the other way. Yeah, no thank you. All right, so there's a little bit about cylindrical. Spherical, we'll tackle that on Monday. We'll look at how do we do spherical, and we'll actually do this same example, but with spherical, so you can see how that one plays out. We are going to have to develop the Jacobian because the Jacobian is very different. There aren't even R's anymore once we're in spherical, so it's going to have to be in terms of rhos and thetas and phis. Anyway, so the Jacobian is different. We will deal with that. But then we'll see that using the conversions, it can make some of these things even easier. Long story short, there are going to be triple integrals that are super fast in spherical. There are others that are super fast in cylindrical. There are others that are super fast in rectangular. It's just a question of which one do we want to be into, you know, what is the region? That's going to really determine what makes one better than the other. All right, so with that, I'm going to go ahead and stop our recording unless there are any more questions on this example.
You said you got that minus 1/3 after you do the u sub.
Correct.
Okay.
Yeah, because there normally would be a 2/3 here, but then you have to divide by -2 that comes from the u sub.
Yep. Okay.
All right.